Alright, so let's take a look at special angles. So special angles are angles that we will actually know the exact value of their ratios for a respective function, like a sine, cosine, tan, or its reciprocal functions, right? And these angles include 0 degrees, 30 degrees, 45 degrees, 60 degrees, 90 degrees, 180 degrees, 270 degrees, and 360 degrees. Okay. Now for the first set of angles, the 30 degrees, 45 degrees, and 60 degrees, we can determine the exact value of their respective ratios for each of the three primary trig functions, right? We can find the exact value of these ratios by using something called a special triangle. Okay, so we're going to be using a special triangle for these three values to demonstrate that. And then for these other values left over, the 0 degrees, the 90 degrees, the 180, the 270, and the 360, we're going to be using something called a unit circle. So I'm going to start with the demonstration of these special triangles, and then we'll take a look at the unit circle, right? Okay, so I'm going to start the special triangle depiction of these special angles. We're going to find the values, exact values of their ratios for 30, 45, and 60 for the sine, cosine, and tan functions. Okay, so let's start with our first special triangle. I'm going to call this special triangle number 1. It's not its particular name, but I like to kind of differentiate between the two. And you guys have to just memorize this. I haven't had to construct it, but this is technically an isosceles triangle. Okay, so let's say that this is your isosceles triangle here, and then this is, and these have to be right angle triangles because these are primary trig ratios. Okay, this is side length of 1, side length of 1, and then this is square root 2. Okay, so I'm just going to clean that up a little bit. Sorry about that, guys. Okay, so this is your right angle triangle. These are the side lengths of 1, right? You can notice that these are the same. And the angles associated are 45 degrees and 45 degrees. We know that an isosceles triangle will have two it's the same size, and as a result, two same angles, right? And we can notice that we can actually find the exact value of one of these angles, because the other angle is the same thing. It has to be an acute angle. You notice that sine 45 degrees is basically equal to, and this becomes a reference angle, so let's just do it here. So this is my opposite side. The hypotenuse is always across from the right angle, so this is the hypotenuse, and this is the adjacent side. So you can actually see here that sine 45 is 1 over square root 2, right? Now this ratio has a radical in the denominator, and we prefer not to have a radical, so I'm just going to multiply by square root 2 to both the numerator and denominator, so you actually get square root 2 over 2. So sine 45 is equal to square root 2 over 2. I'm going to be using this ratio value more consistently because of the fact that it's in better form. And if we take a look at cosine 45 degrees, well, we'll actually see that it's the adjacent side over the hypotenuse, and you'll actually get the same ratio, 1 over square root 2, which is square root 2 over 2, right? And this actually kind of coincides with what we showed earlier, that sine theta is equal to cosine 90 degrees minus theta. Right, so you can notice here that sine 45 degrees is equal to cosine 90 minus 45, which is equal to cosine 45. So they actually have the same ratio. So that's one way we can actually see that, right? So you actually get square root 2 over 2. And tan 45 degrees is basically equal to opposite over adjacent, which is 1. So therefore, the values for the special triangle number 1 here, right, we can notice that sine 45 degrees is square root 2 over 2. Cosine 45 degrees is square root 2 over 2. And tan 45 degrees is 1. Okay, so those are the summary of our values for 45 degrees. I'm just going to make a box here. So make sure you guys memorize this, but really the idea is just memorize this special triangle here. Right, so if you memorize the special triangle, you can actually come up with these values, right? Now, the next special triangle that I'm going to be looking at here is basically going to help us to find 30 degrees and 60 degrees, right? So I'm just going to clear some room here, so I'm just going to erase this out. Okay, so now we're going to look at the other ratios, the exact value of the ratio for the other angles, 30 degrees and 60 degrees, by using these sine, cosine, and tan functions. Okay, so this time our triangle is going to look something like this. Whoops. Okay, so the triangle is going to look like this. And it's going to have a side length of 1, 2, and square root 3. Okay, this angle here is 60 degrees, and this angle here is 30 degrees. Now, a quick way of kind of remembering how to create this special triangle is what we could do here is we take an equilateral triangle. Okay, let's say that this is our equilateral triangle. We take our equilateral triangle, right? I didn't draw the scale, but kind of just bear with me here. Let's say that this is 2 units by 2 units by 2 units, and then this is 60 degrees by 60 degrees by 60 degrees. What we do is we basically take our magical scissors here and we cut this guy in half. Okay, so we cut this guy in half, right? And when we cut this guy in half, we actually create a right bisector. Okay, so when you create a right bisector, what happens here is you create a 90-degree angle, and when you cut this in half, look what happens, right? So you basically end up with this. You can see that the 2 unit is retained. This guy becomes 1 unit, and half of the 60 degrees is going to give you 30 degrees, and you also create this 90-degree angle. So this is a right angle triangle, and that's how you get this triangle. So that's a good way to memorize it if you guys, need some kind of backstory to help you with that. And then we can figure out some of our ratios. So let's start with our reference angle of 30 degrees. Okay, so I'm going to start with 30 degrees here. Okay, and in this case, now this becomes the opposite side, right? Across from the right angle will always be your hypotenuse, and then this guy, as a result, will become the adjacent side. Okay, so now we can see here that sine 30 degrees is equal to opposite over hypotenuse 1/2. Cosine 30 degrees is equal to adjacent over hypotenuse, which is square root 3/2. And tan 30 degrees is equal to opposite over adjacent, which is basically 1 over square root 3, or you can write this, if you multiply by square root 3, as square root 3/3. This is more preferable, right? So we have our values of 30 degrees for each of these trig functions. Now let's take a look at the 60-degree version, right? So if we take a look at the 60-degree version, I'm going to just get rid of this, just get rid of the coloration here. Whoops, got rid of our entire triangle by doing that. Okay, so let's say this is our triangle, right? And basically we can note here that the hypotenuse would be conserved, right? Still 2 here. And this time we'd be looking at 60 degrees. Okay, so let's take a look at this angle now. Okay, so if I'm looking at this angle, right, this is the opposite side. So I'm just going to erase this. So now this guy becomes the opposite side. The hypotenuse is still conserved, and this is your adjacent side, right? So now you can see here that sine 60 degrees is equal to opposite over hypotenuse, square root 3/2. Cosine 60 degrees is basically adjacent over hypotenuse, which is 1/2, and tan 60 degrees is equal to square root 3/1. You can also see that this cofunction identity is still conserved, right? Now we can see that sine theta is equal to cosine 90 minus theta, and cosine theta is equal to sine 90 minus theta. And you can notice this by just kind of comparing these two, right? Like if I compare sine 30 with cosine 60, they'll have the exact same value, right? But also if I compare this cosine 30, if I compare cosine 30 with sine 60, you'll see that it has the same value as well, right? So this will kind of work for all scenarios, right? And these are our values of our special triangle.